Greetings, everybody. So we are continuing our videos on chaos-based image encryption, and the topic of today's video is local entropy, which is basically a continuation from our previous video regarding entropy. So let's begin. Again, I'm reminding everybody that we're talking about symmetric chaotic encryption here. This means that I have a chaotic source at the transmitter. I'm using it to encrypt some sort of plain text information, like an image, then safely transmit the encrypted information through a public channel, and back at the receiver end, I'm using the exact same chaotic source, using the exact same key values in order to reverse the encryption process and obtain the original information signal back. So the classic, of course, uh, actions that we perform for encryption are permutation and substitution. Permutation basically means shuffling the pixels of an image in order to disperse the information throughout, and substitution means taking each individual pixel value and replacing it with another value. So, again, as I told you in the previous video, entropy is a statistical measure from information theory, and it measures the amount of information present in a time series, or if you like, how predictable or unpredictable or uncertain, if you like, this time series is. Okay, so this can be considered for any time series, and an image practically is a time series. So for a gray image, the entropy value is on the highest possible value is 8. Okay, so obviously an encrypted image should have the highest possible entropy. So its entropy, as you see on the bottom right here, for the encrypted image is very close to the optimal value, which is 8. Okay, while actual images that contain some sort of information have a somewhat lower entropy. Okay. So what we discussed in the previous video is like for plain text images where we perform shuffling, the entropy is computed for the image as a whole. So it takes this image, it transforms it to a one-dimensional time series, computes its entropy. So the original and shuffled images have actually the same amount of entropy. One might think that, okay, the shuffled image makes no sense to the naked eye, so how can it have the same amount of entropy? Well, this is because, as I explained, entropy is computed on the time series as a whole. So permutation of the elements will have no effect on the entropy, okay, as an overall time series, okay. And a solution to that is an alternative measure, which is called local entropy. So what is local entropy? Basically, the idea behind local entropy is to take an image, like the peppers as you see right here, and break it down and take from this image and extract some sort of smaller images, which are basically blocks that are very important. They are not overlapping. Okay, as you see right here, I have a collection of different sub-blocks from the image, and none of them are overlapping. And what we do for local entropy, we take all of these sub-blocks, we compute the entropy of each block, and then we take the average of all these entropies. Okay, so here, for example, I take 30 blocks, and each of these are size 44 by 44 pixels. So overall, there are 44 squared pixels in each sub-block. Okay. You can take other values, but this is very common in the literature, and this is why I take it as well. So these are the overlapping blocks right here. I choose them randomly, and I will attach a MATLAB code on how to do that. Of course, you can take any number of different non-overlapping blocks. So as I run my simulation again and again and again, each time I take a different set of 44 blocks. Okay, not 44, sorry, 30 blocks. So I take the entropy of each block and then I average it. And now, as you see, for the entropy, while the original shuffled images had the exact same amount, now for the local entropy, we see a difference. Okay, the plain text and shuffled images have a different local entropy, 6.18 for the original and 7.48 for the shuffled image. So much, much higher. And this is an indication that we indeed managed to disperse the information throughout the image, right? So this is a very good result. Of course, both for the entropy and local entropy, the encrypted image has the highest amount, okay, 7.99 for the entropy, and for the local entropy, 7.90. Okay, so in all situations, you should take that for granted. The encrypted image should always have the highest amount of entropy, okay? But for the local entropy, this is what we managed to do here, right? We managed to obtain a highest value compared to the original image, okay? And this is what we should always achieve, okay? What in the entropy as a whole, we cannot achieve that, I'm sorry. For the local entropy, we successfully achieve this, okay? Of course, as you can understand, same thing happens for color images. We have 3 channels, so you can take the entropy and local entropy of each individual channel, okay? Here, of course, I need to remind everyone, as in the previous video, we have a specific technique where we combine all the channels together and then shuffle the pixels. And that's why here, since this is a very nice technique, again, in the case of entropy as well, we have different entropies for the original and shuffled images. But again, for the local entropy, we achieve the same result. The shuffled image in both cases has higher amount of entropy and local entropy compared to the plain text image. And of course, in all situations, the encrypted image has the highest entropy and local entropy in all 3 channels. Okay, again, this is the desired result, so we have a very nice encryption. Okay, so this is the difference between entropy and local entropy. And in the description of the video, I'm going to add some MATLAB codes in order to compute both types of entropies. So thank you very much and see you in our next video.